Hey everybody, just a couple of words about exercise 3 on page 28. They've given us a few fractions and the instructions are express the fractions in sexagesimal notation. So in other words, expressing it as the sum of coefficients times various powers of 60. For example, this number, sexagesimal notation, would be 2 times, holy moly, I don't know, 60 to some power plus 3 times 60 to some power plus 15 times 60 to the 0 power. Okay. The semicolon is adjacent to 60 to the power of 0. So this is going to be 3 times 60 to the power of 1. This will be 2 times 60 to the power of 2, and so forth. Oops. Did I account for this one? I sure did not. Plus 4 times 60 to the negative 1. So they're asking us to express the fractions that they give us in sexagesimal notation, this kind of notation. And before we do that, I thought it might be helpful to go over something that we're going to see in this course anyway. But I might as well just let the cat out of the bag for our use right now. It's something called the division algorithm. Intuitively, we know this. Essentially, we know how to perform the division algorithm without being aware of its theoretical significance. Given integers a and b, with b greater than or equal to 2, there exists a unique pair of integers, q and r, such that r is greater than or equal to 0 and less than b, such that a is equal to q times b plus r. And let me diagram what these things are now. A is the dividend. Q is the quotient. B is the divisor. And R is the remainder. And now that we've identified some of the main characters like quotient and remainder, these conditions kind of make sense. When we divide an integer a by a divisor b, we could get a remainder that's 0. If we get a remainder that's 0, that just means that A is a multiple of B. If we get a remainder of 0, that means R is 0, and that means that A is equal to Q times B. It means that A is a multiple of B. So the remainder could be 0, in which case A is a multiple of the divisor B. Now suppose that the remainder is not 0. Then it has to be a positive integer less than the divisor. And this makes sense. We don't do this. 26 divided by 2 is equal to 8 with a remainder of 10. Let's see, 8 times 2 is 16, plus 10 is 26. But we don't say that 26 divided by 2 is 8 with a remainder of 10. We say that 26 divided by 2 is equal to 13 with a remainder of 0. Similarly, let's look at this. 45 divided by 7. Okay. Here's what we don't say. We don't say that 45 divided by 7 is equal to 5 with a remainder of 10. Now it's true that 5 times 7 is 35, plus 10 is equal to 45. But when we divide 45 by 7, we expect to get a remainder that's less than 7. So the correct way to do this would be to say 45 divided by 7 equals 6 with a remainder of 2. 7 times 6 is 42. Let's say with a remainder of 3, shall we? 45 divided by 7 is 6 with a remainder of 3. Now this looks good because the remainder is less than the divisor. 7 times 6 is 42, plus 3 is 45. It works, and the remainder is less than the divisor. So in the division algorithm, to stipulate that the remainder is non-negative and that the remainder is less than the divisor is just saying that when we divide one integer by another, we do it the way we've been doing it since second grade. We weren't taught it in this manner in the second grade. Essentially, we were taught by example how to do it. We were taught that our remainder should never be equal to or larger than our divisor. But the division algorithm just states that we do division of integers the way we've been doing it since second grade. And the division algorithm here, I think, is going to be helpful in page 28, example 3. A couple of you did exercise 3 using the division algorithm. A few others of you used other clever means of doing it. But I'd just like to go over some of the exercises that may have been problematic. Exercise 3B, express 1/9 in sexagesimal notation. The troubling thing here is that the denominator isn't a multiple of 60. And you know what? 9 doesn't divide 60. 9 is not a factor of 60. So we can't multiply top and bottom by any number that will give us something over 60. 9 has two factors of 3. This is 3 times 3. 60 has one factor of 3. The other factor would be 20. So what I'm thinking here is, for each factor of 3 that we have in this denominator, we're going to have to multiply top and bottom by a factor of 20 to give us 60. We have 3 squared in the denominator, 2 factors of 3, and that means we're going to have 2 factors of 20 in the denominator. Nope, let's see, 60 squared, that's what that is. Okay. Now we have the denominator as a power of 60. That's good. If we square the numerator or simplify the numerator, we have 400 over 60 squared. If we're in sexagesimal notation, the coefficient of 60 to the negative 2, or the coefficient of any power in sexagesimal notation, should be between 0 and 59. We have base 10 decimal notation. Our coefficients are always between 0 and 9. Base 10, our coefficients, our digits are 1, 2, 3, 4, 5, 6, 7, 8, 9. Base 60, our coefficient should be 0, 1, 2, 3, 4, 5, dot, 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 58, 59. So the denominator is too large. What I would like to do is the numerator is too large. What I would like to do is express this in terms of powers of 60. And to do that, I'm going to use the division algorithm. But what's Q here? If Q is 5, we get 300, okay. If Q is 6, we get 360. If Q is 7, we get 420. Oops, okay. It looks like Q is going to be 6. This gives us 360 with a remainder of 40. My numerator is still too large. Having 40 in the numerator, that's fine. It's smaller than 60. Having 6 times 60 in the numerator, that's no good. It's bigger than 60. I'm going to write this as 2 separate terms. 6 times 60 over 60 squared plus 40 over 60 squared. Oh, and isn't this nice? The 60s cancel out, and we get 6 over 60 plus 40 over 60 squared. Excuse me. have no whole number multiples of 60. We have a multiple of 6 times 60 to the negative 1, and a multiple of 40 times 60 to the negative 2. So in sexagesimal notation, this is how we would write 1/9. Before we move on to one of the other exercises, I'd like to do this a way that some of you chose to do it. It was a nice way to do this. You took a look at this and you said, well, let's see, there's no whole number that I can multiply 9 by to get 60. But apparently we reasoned that if we divide 9 by 3, that gives us 3, and then multiply by 20, that's going to give us 60. And so what some of us did, and this is a pretty good idea, we took 1/9, and then we multiplied the denominator by 20/3, the numerator by 20/3, and son of a gun, this is, the 3's cancel, so it's 60 in the bottom, and 20/3 on top. Well, it's not a whole number in the numerator, but we're not done yet. And as a next step, those of you who did it this way, you said, you know what? This is a whole number plus something a little bit less than a whole number. We can write this, well, division algorithm. 3 goes into 26 times with a remainder of 2. And then we said, the 6 over 60, that's fine. We can leave that. This 2/3 over 60, that's what we're going to worry about now. And we reasoned, well, if we multiplied top and bottom by 60, that would make the denominator 60 squared, which is a good number. It's a multiple of 60. And we're going to get a whole number when we do this. We're going to get 6 over 60 plus 2/3 of 60 is 40 over 60 squared. And this is looking real good. A positive number between 1 and 59 over 60. A positive number between 1 and 59 over 60 squared. Ooh, this is looking real good. We don't have any whole number divisor, but our divisor is 6 times 60 to the negative 1 plus 40 times 60 to the negative 2. 40 times 60 to the negative 2. So that was a nice way to do it also. And I think you'd appreciate seeing it both ways. Doing it my way, we got a chance to look at the division algorithm a little bit prematurely, but maybe that's a good thing. Doing it this other way, we're exposed to another way of thinking, a good way of thinking, and that's good also. The way we improve as mathematicians is we take everything that we see other people do that's effective and correct, and we integrate it into our own repertoire. That's the way all people become very good at math. So I wanted to show both ways of doing this. Let's take a look at 3D. Express 1/24th as a fraction in sexagesimal notation. Okay. Or express it in sexagesimal notation. Again, we see the problem. There's no number that we can multiply the top and the bottom by to make the denominator equal to 60. Or maybe I should say there's no natural number, no whole number, that we can multiply the top and the bottom by to make the denominator 60. And I guess what I'm doing here is I'm going to figure out what I have to multiply top and bottom by to make the denominator a higher power of 60, 60 squared or 60 cubed. So let me write this as a product. And I'm going to write this as 1/6 times 1/4. And you know what? If I just had this fraction, I could write this as something over 60. I just have to multiply top and bottom by 10. And if I only had this fraction, I could write that as something over 60. I just have to multiply by 15, top and bottom. So you know what? I'm going to do that. I'm going to take 1/6 and multiply top and bottom by 10. And then I'm going to take 1/4 and multiply top and bottom by 15. And son of a gun, I get 10 over 60 times 15 over 60. And that's going to give me 150 over 60 squared. Okay, I got a power of 60 as the denominator. But the numerator is not a whole number between 1 and 59, or 0 and 59. So you know what? I'm going to apply the division algorithm to this son of a gun. 150 is equal to something times 60 plus something else, let's see. As a divisor, 60 goes into 152 times. That gives us 120 with a remainder of 30. And I'm going to take this thing, 150 over 60 squared, and I'm going to write 150 as 2 times 60 plus 30, all over 60 squared. My numerator is still larger than 59. So as a first step to remedying this, I'm going to take each of the terms in the numerator and write them separately over the denominator. So I should get 2 times 60 over 60 squared plus 30 over 60 squared. And oh, this is so nice. The 60s here cancel out again. Son of a gun. And that leaves me with 2 over 60 plus 30 over 60 squared. And we could write it this way. 2 times 60 to the negative 1 plus 30 times 60 to the negative 2. This fraction doesn't have a whole number part. So we write a big fat 0 and a semicolon. And the coefficient that goes right here is the coefficient of 60 to the negative 1. That's 2. Then the coefficient that goes here is the coefficient of 60 to the negative 2. That's 30. So there's our answer. 1/24 in sexagesimal notation is 2 times 60 to the negative 1 plus 30 times 60 to the negative 2. Now, did everybody do it that way? No. So let's see how some of you did do it. Here's what some of us did, and it was a pretty good idea. Apparently we reasoned, I want to multiply the denominator by something to make it equal to 60. Ooh, the only problem is 60 is not a multiple of 24. And then maybe we realized, you know what, 5 times 24 is 120. 5 times 24 is 120. And that's twice as much, that's twice as big as we want it to be. If we multiply this by 5, we get 120. We want it to be 60. So apparently we said, you know what, let's just cut it in half. We'll multiply top and bottom by 5 halves. And son of a gun, we get 5 halves over 60. So the denominator is 60, and that's exactly what we want. The problem is the numerator is not a whole number. And we like the coefficient of 60 to the negative 1 to be a whole number between 1 and 59. So we'll write it like this. 5 halves is equal to 2 plus 1 half over 60. This part of the numerator is fine. It's a whole number. This part isn't. And so what we do is we split up the numerator. And apparently this part is supposed to be something times 60 squared. And we reasoned, you know, we can say, well, we got 2 over 60 plus 1 half over 60. And multiply top and bottom by 60. That will give us a denominator of 60 squared. And in sexagesimal notation, the coefficient of 60 to the negative 1 is 2. The coefficient of 60 to the negative, the coefficient of 60 to the negative 2 is 30. And there we go. In sexagesimal notation, 1/24 is equal to 2 times 60 to the negative 1 plus 30 times 60 to the negative 2. So some of us opted to do it that way, and that was a pretty good idea. Let's look at one more, okay? Okay. Take the fraction 140, express it in sexagesimal notation. The first problem that I see is that 40 is not a divisor of 60. So there's no whole number that we can multiply top and bottom by to get 60. So what I'm thinking is multiply 1/40 by something to give us 60 squared in the denominator. There's nothing we can multiply 40 by to get 60, but there should be something that we can multiply 40 by to get 60 squared. And to facilitate that, let me write 40 in factored form. Let's see, 40 is 8 times 5, right? And 8 is 2 cubed. Now what about 60? 60 equals 4 times 15, which equals 2 squared times 3 times 5. This is the prime factorization of 60. And here's why 40 is not a divisor of 60. 40 has 3 factors of 2. 60 only has 2 factors of 2. So 40 cannot be a divisor of 60. But what about 60 squared? That should be 2 squared times 3 times 5. This is 60 squared. So that's going to give us 2 to the 4th plus 3 times 3 squared times 5 squared. 60 squared has this factorization. So what I propose is I'm going to take top and bottom here and multiply top and bottom by all the factors of 60 squared that aren't present here. We have 1/2 cubed times 5. But 60 squared has 4 factors of 2, not 3. So I'm going to multiply top and bottom by 2 to give the denominator that 4th factor of 2. Also, 60 squared has a factor of 3 squared. You don't have any factors of 3 here. So I'm going to multiply top and bottom by 3 squared. And then we have a factor of 5 here. But 60 squared has 2 factors of 5. So I'm going to multiply top and bottom by that missing factor of 5. And holy moly, let's see what I get. 3 squared is 9 times 5 is 45 times 2 is 90. And the bottom, we're going to get 2 to the 4th times 3 squared times 5 squared. And that's going to give us 90 over 60 squared. You know what the problem with this is? It's a number bigger than 59. We've got to chop it down to size. And we're going to use the division algorithm to do that. We're going to take our numerator, which is too large, it's larger than 59, and we're going to divide it by 60. Okay, 60 goes into 90 once, with a remainder of 30. Excellent. So I will write this as 1 times 60 plus 30 all over 60 squared. And then I'm going to split the numerator up and write each term of the numerator separately over the denominator. And wouldn't you know it, the 60s cancel again. So we'll get 1 over 60 plus 30 over 60 squared. And we could say 1 times 60 to the negative 1 plus 30 times 60 to the negative 2. And in sexagesimal notation, that's a big fat 0, semicolon. 1, 30. Now, let's see how some of us chose to do this, an alternate way. Same exercise. Here's what some of us chose to do. They said, there's no whole number that we can multiply 40 by to get 60. What number can we multiply 40 by to get 60? And they reasoned 3 halves. And so they just multiplied top and bottom by 3 halves. And they got 3 halves over 60. There's no problem with the size of the numerator here. The numerator is between 1 and 59. But it's not a whole number. So they just rewrote the numerator as 1 plus 1 half over 60. And then wrote each term of the numerator separately over the denominator. And then they reasoned, you know, we have to make this a whole number. If we multiply top and bottom by 60, the numerator will be a whole number. The denominator will be a power of 60. Looking Looking good. And we can write this as 1 times 60 to the negative 1 plus 30 times 60 to the negative 2. And in sexagesimal notation, 0 whole numbers, 1 times 60 to the negative 1, 30 times 60 to the negative 2. So some of you did do it that way, and I enjoyed seeing that. This was a good way to do it. Of course, it'd be nice if maybe we could do it both ways. Not only will we know how to do it, but we'll be taking our own way of thinking, which might be this way, and augmenting that with somebody else's way of thinking, the first way that we did it. And we will add that thinking to our mathematical repertoire. Well, that'll conclude this video. In the next video, I'm going to talk about false position and double false position.